Stuxnet came out, the paper, the whole world went crazy, and it felt as crazy as today, believe it or not, even though it was back in 2012. Everyone was just saying, look, the cats are finally recognizable by Google speech and everything, and all this craziness was going on around, and of course agitation got into us as well, and so we started asking simple questions. Well, can this deep learning do something what we already know, something what we already do? Like, can we use it instead of ICA? Well, can it do more than we're doing right now? And what can it do for subject populations? But do we have enough data for deep learning? We're not Google, we have some data. And so what can it do for single subjects maybe? Well, basically you can figure out we were confused. And the main question that came out, and that is still on the table, is can we learn from the model something about the data that we did not explicitly teach it? That will be knowledge discovery by the model that teaches us something that we didn't know and that we didn't train it to do. The interesting task that usually interests engineers in computer sciences is if we can do something, can we just let deep learning or AI, whichever you like to use, do it for us? But I argue for science, it's more interesting to us is discovery. Can it do something that I cannot do? Can it discover something, or can it help us in the discovery? So we heard at the time that, how deep learning works, it takes simple images and then separates somewhere in the internal representation space into concepts, say, first layer CNN detectors are edge detectors, Gabor filters, and it learns to have them like that, and then eyes and parts of cars if you train them on car spaces, etc. That's like, oh yeah, that's cool, that's interpretable. But what if you train it on an fMRI? For example, with my background, I wouldn't be able to distinguish good feature from bad feature, or is it a good aggregated feature? Why deep learning took off so easily? Because it was applied to images, and we are very good image recognizers. We could see its learning, but if it was initially applied to some basic data like fMRI, probably it wouldn't be where it is today. Well, I should be looking at that. Well, anyways, so the question was, well, how do we figure out if deep learning is doing something useful, not just predicting and giving us high accuracy? And that's around 2012 to 2013. And we came up with this idea. That's a simple idea. You've heard of it before, but I have to go through it for historical reasons. MNIST dataset, everybody's seen that. If you represent each point in the MNIST dataset, each digit, each point, each sample on this plot, then there are methods that can give you this layout. And this layout kind of looks structural, but it's meaningless unless you put the colors on it that signify the meaning that what does this digit represent, what this number represent. And then you see, hey, there's structure in the data. This is so good, so interesting. So the question was, can we look at the data of internal representation of deep learning, whether it's learning something interesting in the structure? And we looked at FBERM dataset, 400 brains, schizophrenia versus healthy control, and this nice animation from, from left to right, the same. So on the left is when we're trying to classify or represent raw data. When you try to represent raw data in the 2D space, each point is a volume, is an MRI volume, gray matter constellation map rather, but it doesn't matter for this purpose. It's just represented by a point. And relative location supposed to be meaningful, but here the algorithm that tries to lay out all the subjects in one space just doesn't converge anywhere. This is one layer neural network. This is two layer neural network. This is three layer neural network. And so just to avoid dizziness, what I will, I'm showing it on my screen. So raw data, just a mess. And there are four colors here, training data and unseen test data. Unseen test data is green and blue. And we saw back in 2012-13, around that time, that the deeper network, the deeper is the network, the more separate are representation of the subjects across schizophrenia and healthy control. So the more separate there are, the easier it is to classify outliers, something in between. Okay, well then we went further. We took, that's kind of big data-ish for neuroimaging, even still now, 3,500 brains for Huntington's disease. And Huntington's disease is genetic and actually very well quantifiable, so there's this path sequence. If it's repeated too many times, a person has Huntington's disease. The problem with Huntington's disease, you can identify at birth from the baby that the baby has Huntington's disease, but the question is when will it kick in? And if Huntington's disease, it's grandmother deterioration, cognitive loss, etc. So because we don't know when it kicks in a given person, we developed, well not we, the field developed this CAP score, CAG length, it's number of repetition of CAG times age. And at low score, there's no, t-test doesn't tell you the difference between healthy brain and low score Huntington patient. At median score, okay, we have deficit, it's already visible, and high score, large deficit, but still not clinically diagnosable. So, healthy control versus median, we see some differences, deterioration, and high, we see a lot of differences. So what we did, we trained neural network, what was DB and deep belief network at the time. This is the time when there was no PyTorch, no Theano, not even Theano, if anyone remembers, not TensorFlow. And here's what we found. After training to classify the patient, all the patients, we took the representation that the network forms at its last layer. It's still multidimensional, and each point here is that representation mapped into 2D space. And we trained a classifier, binary classifier, Huntington, non-Huntington. Easy information, we know it exactly because it's genetic. That's all that neural network knew. It took gray matter concentration maps for each patient and trained that classifier. Then we mapped this representation, and we were surprised to find, after adding colors here, those colors here, this gradient, is the CAP score, the severity of the disease, basically. And network kind of stratified, you see the gradient, we didn't teach it. And that was kind of, that was a positive sign for us back in 2013, we published it in 2014. This paper. We had repeated this type of analysis later with schizophrenia spectrum disorder, and you can also see that depth 1 network is not structured, and depth 3 and further network is already structured. So the point here, historically, when we started looking at deep learning, our question was not improve the classification rate, but can we learn something? Can it go through, sift through big data? And if it learns to do good prediction, then maybe we can learn from it something. How does it do it from the data that we are unable to use for prediction? So now, fast forward. So the status quo in our field and in machine learning conferences, but neuroimaging subfields, we see lots and lots of papers. This is the subplot. I will talk about the plot later. It's just an illustration for now, but it will become actionable on the next slide. Everyone is developing a better model, and they call better is more accurate model, right? If it gives you better classification, this is a paper, and that's all people usually hear about, at least in my subfield where I'm looking at. And we have two types of models here. Models that work from time series data, because we want to learn about time series and about dynamics. And models that learn from functional network connectivity, from correlation matrices. And three of those models are million parameters, large deep learning models that are created to be better classifiers for offensive. And this is good old logistic regression that every one of you knows, and I hope loves, because it's one of the best classifiers if you look at functional network connectivity. And it is an interpretable classifier. You know exactly what it does, and you know exactly what's good about the predictions. But there is another classifier there, and Pavel here has developed it. We call it mean MLP because we average multilayer perceptron flat the same multilayer perceptron just applied at each time point. And very simple classifier, and it is here, and it's among the best across logistic regression and classical machine learning. Doesn't work on time series data that well because the dimensionality is large, cursor dimensionality destroys it. But the point of this work is that classification accuracy in any metric shouldn't be the driving force. And I'm sorry of moralizing here, but it shouldn't be, that's what I believe, for publication or for research, because even simple models can give us very good classification accuracy. What's the point? It doesn't mean he avoids deep learning. Deep learning is very useful because we can learn from deep learning, we can obtain interpretation why deep learning models do this or that prediction. Our model here, mean MLP, is uninterpretable. It's very hard to figure out what it's doing. It has tiny number of parameters. You can easily train it or use it. You install ML for MRI and models language. But those deep learning models, if you train them and you learn from them, this is good. This cartoon demonstrates this kind of thinking. If we can pre-train a model, and then we can train a model to predict and classify, and then we can, usually the field takes another model that interprets this model we just trained, or tries to extract some information, interprets to us, okay, here's what the meaningful stuff that the other model learned. And the field, as the previous speaker also mentioned, interpretability boomed. We just published this survey paper on interpretability in machine learning, and it's off screen, the actual reference, and neuroimaging. Lots of categories of interpretability, lots of methods, and lots of applications to neuroimaging as well. But let me do one sort of definition and introduction. Interpretability or explainability, people use them interchangeably. For the purposes of this talk, when I say explainability, I want to explain the data. I have a sample, why this sample was classified as disease versus healthy. Interpretability is when I look at PCA, I want to understand how it works, and I pretty much do. Right? I can interpret what it does and everything. So, but instead of building additional, not the keyword of this talk, instead of building additional models that will help us interpret other models, we argue and introduce architectured interpretability, ArcInterp. Let's build models that are deliberately interpretable to us from the beginning. And how do we do this? Well, let's arbitrarily assign something to be interpretable. And I argue that graphs are naturally interpretable. Every time we try to explain something, we draw a graph. Genetic network, okay, it's graph, relationships. Network of chess games, it's a graph. So every time we try to explain, it usually ends up being a graph. And even a lot of talks yesterday about connectivity, it's also a graph. So because graphs are naturally interpretable to us, philosophy network and tree is a graph as well. And neural network, if it's a small neural network, is a graph. That's a joke. Interpretability with a graph. Here's the suggestion or the program that we're following. When we have a system that we don't understand, we tend to make a window inside of that system, something transparent that we can look inside of that system, like this rat is being observed by researchers on this picture. So the suggestion and the program that we're pursuing now is, I can fast forward, take black box model and forget, like just use it, because black box models are powerful. Don't try to look inside of this model. This is an encoder. Let it be black box. It takes the input and does what it does. But it has to produce something interpretable, in our case, a graph, that we can look at. And this graph is the only thing that the decoder will take. If there is no bypass, there is no cheating involved. The encoder, by looking at the data, has to encode entire information in a graph so that the decoder can produce good prediction. Prediction is fine from this graph. But then we can look at this graph. Let's keep the model architectures. And we can look at this graph and get interpretable information. We train the same model on the same data, but to do different tasks. So we train the same model once on the data to predict gender. Then we took the same data, we started the model from scratch and trained the model to predict on the same data to predict age. And we see one of them, okay, this is static Pearson correlation. And those are age, gender, and dementia classification. The same model, the same data, only predicted to do three different things. And it gives us interpretable graphs that are related to what we trained the model to do. We can get an average, or we can get it for each subject. And so this approach, ArcInterp, I'm not going to talk about this model, but basically you build in something interpretable to the model from scratch before you start to train it. Then when it's trained, you can analyze and get interesting results that we're getting. So what's next? Quickly, I have a minute that I will be able to say that. And there was a discussion yesterday about counterfactuals. So if this model, now multimodal, learns this graph, notice that there's only one path from any input to the output. It goes through the graph that we will understand. We will look at it and we understand what it means. But when this model produces good results in any of those variations, we can use this graph as a counterfactual model, because each node of the graph means something to us, and we can clamp. It's not a real experiment, but it's a counterfactual world modeling. We can change the model and see how the prediction will change, and that will help us to generate hypotheses. If the model is a good prediction, and we could say, well, what if we modify activity in this region? What happens then? The prediction changes. Well, let's maybe go to wet lab and try that experiment and see if that prediction is true and if nothing works. So it's kind of a world model. ArcInterp is the keyword that you should remember from my talk, and this is my team that worked on all of that, and they kind of slowly leading, growing up and graduating. Yeah, that's what the arrows and the spiral represents. Any questions?
Yeah, so I was wondering what you think about, you said that you're not impressed by creating a better model.
Better classifier.
Yeah, better classifier. But what do you think about throwing in more parameters, more parameters, like more NVIDIA chips? Do you think that could be different, that it actually...
But what for? To get better classifier?
Exactly.
Well, we can beat you with logistic regression.
No, actually, to be used more like a real human, I would think, is the reason.
You're talking about general AI?
Yeah.
Well, if it does the job, if it works, why not?
But do you think it will work if you just like have like twice as many GPUs or NVIDIA chips as we currently have? Do you think that will?
Well, seriously, I don't think that it will work just that way. It's like throw data into a pile of linear algebra and eventually it will
Right.
work. But exploration, exploitation, we have to stop sometime and think. I can't say like only theory works, and I can't say only experimentation works. It doesn't need to work. And this approach, the approach that you're describing,
Yeah.
scaling laws,
Right.
it's working, so it's useful to some extent.
So I have a question. So, in your talk, you talked about sort of having to be transparent and having, clear what worked, what didn't work in the models. But I think it even would be more useful, like the whole time I was thinking about, what were the features and how do they map to the brain and how would you describe them, as opposed to just, that very end you had that, circle sort of, connectivity graph. Even that is sort of opaque in some sense in terms of, I think that would help disseminate this if you had some way of being further being transparent about what features were actually useful. And because then you can use those features to learn something about the brain, as opposed to just, it's still hard to interpret those graphs and matrices. Actually having something on the brain that says, okay, this is what drove this differentiation. That would be useful.
Yes. Well, but if we go back to here, if
Yeah.
you can trace, what you're saying is you need to prove that this ROI that we are denoting as a node in the network has connection to the ROI in the data that you
Right,
think.
that's actually driving the decision of the algorithm.
Well, the decision may be driven by interaction, by second, third order. But at least you know what is interacting. That's how I understand. And the methods, like this model that I'm suggesting or proposing, or this approach, can be also post hoc analyzed. Like, okay, well, this is a node of your graph, but what drives that node? We tend to build, try to build the models where that connection is implicit or explicit rather. You know, okay, this node represents this brain region, but it can be examined for, like, verified. It can be verified. But at least that's the point.
Thank you, sir.
Thank you.